Now we're going to look at the development of saddle point bounds for generating function coefficients using contour integration. Well, the basic idea is very simple. We start with Cauchy's coefficient formula, which says that given an analytic function g of z, the coefficient of z to the n in g of z is 1 over 2 pi I integral over a circle that contains the origin, g of z dz over z to the n plus 1. Just to look at an example, let's look at the function. Suppose g of z is e to the z, and we're looking for coefficient of z to the fifth. So that means the function that we're integrating would be e to the z over z to the sixth. That's a plot of that function. It's got a pole at 0, and then as the real part gets large, it starts to get large. And there's obvious saddle point in there. Now, this plot is actually scaled substantially. I think that it's only a thousandth high or something. We'll see some of the numbers in a minute. But still, that's what it looks like. So the idea of a saddle point bound is to find a saddle point, and we always use zeta, the Greek letter zeta for the saddle point. And then for our circle, we'll use a circle of radius zeta. So this is what the integral will be adding up the height under that circle. And as you can see, for most of the range, it's very, very small. But even so, if we just take the highest point of the circle, which is the saddle point, the integrand is going to be less than the value of the function evaluated at zeta everywhere on that circle. So then the value of the integral is just going to be as if we had that constant, and that'll give us a very strong bound. Now, what's zeta? It's the solution to the derivative of this function equals 0. And that's just doing the math. It's g prime over z to the n plus 1 minus n plus 1 g over z to the n plus 2 multiplied by z to the n plus 2, we get z g prime over g is n plus 1. That's known as the saddle point equation. So that's the idea. Find zeta and just use the bound g of zeta over zeta to the n plus 1. So let's take a look at a couple of, well, here's a formal statement of the bound. So if G is analytic, finite radius convergence R, it's got non-negative coefficients, which are generating functions from analytic combinatorics always do, then coefficient of z to the n and g of z is less than or equal to g of zeta over zeta to the n, where zeta is the saddle point. That's just a formal statement of the equation. And again, it just is by Cauchy coefficient formula, you take C to be a circle of radius zeta and change to polar coordinates. Then we get an extra zeta, and then if we integrate and everything's constant, then the 2 pi goes away, and all that's left is g of zeta over zeta to the n. So that's a effective bound that we can use to at least understand something about the growth of generating function coefficients. For example, in our example, we're trying to find coefficient z to the fifth in e of z. So that's, we're looking at e to the z over z to the sixth. What's the saddle point? The saddle point is zeta equals 6. So saddle point equation is g prime over g, which comes out to be 1, leaves just zeta equals 6. And so the saddle point bound says that we know that coefficient of z to the fifth e to the z is 1 over 5 factorial. The bound says that that's going to be less than or equal to e to the sixth over 6 to the fifth. And if we just compute those, on the left side it's 0.008, and on the right side it's 0.009. Pretty good bound, even for just a small value 5. So in general, just doing that same calculation, let's see how well the saddle point method works for estimating 1 over n factorial. So that's coefficient of z to the n and e to the z. E to the z is a generating function with no singularities. We're trying to estimate the coefficient of z to the n in e to the z. So saddle point methods, we take g of z equals e to the z, solve the saddle point equation. Saddle point equation is g prime over g times z equals n plus 1. So it's going to tell us that the saddle point is zeta equals n plus 1. And then the bound is just e to the zeta over zeta to the n, which is e to the n plus 1 over n plus 1 to the n. So that's the saddle point bound. Now, since n plus 1 to the n, if you want to do a little more accurate asymptotics on that, 1 plus 1 over n to the n goes to e, so that's about e to the n over n to the n. And I'm just doing this sketch now because we're working with bounds, so we can be more precise and carry it out to more asymptotic accuracy if we wanted. And so this is just to check how close this bound is to what we know. Well, what we know is from Stirling's approximation, 1 over n factorial is about e to the n over n to the n square root of 2 pi n. So we're off, this bound is too high just by a factor of square root of 2 pi n, which is not bad considering it grows exponentially. So we get a pretty good approximation to the function with this really simple bound. So that's the saddle point bound. And the saddle point method, what is going to be just about getting rid of that factor, finding an approximation that's more accurate and brings that factor back in. Let's look at another example. Suppose we want to estimate 2n choose n. So that's the coefficient of z to the n in 1 plus z to the 2n. So now we'll just take g of z to be 1 plus z to the 2n. The saddle point equation is to take the ratio of g prime over g and set equal to n plus 1. So in this case, that works out to 2nz equals n plus 1 times 1 plus z. Or the saddle point is n plus 1 over n minus 1. So that's where the exact saddle point is. And then the saddle point bound is to take g of zeta over zeta to the n, so n plus 1 over n minus 1 to the n. And then g of zeta is 1 plus that to 2n and work it out. Then we get 4n squared over n squared minus 1 to the n. And again, that's about 4 to the n. And how close is that to what we know? Well, we know that 2n choose n is about 4 to the n over square root of pi n, as we did from Stirling's approximation early on. So again, the bound is off too high only by a factor of about square root of pi n. Simple method for estimating the value of coefficients just by determining the saddle point and then plugging in that value to the function, divide by that to the nth power. And it's off by a little bit, but not much considering the exponential growth. That's the development of saddle point bounds.